In the previous video, we saw that conditionally convergent series are not commutative. That if we reorder the terms, we can get dramatically different results, to the point that we know that we can reorder the terms of a conditionally convergent series in such a way that they add to any number we would like it to add up to. In this video, we're going to see that absolutely convergent series are very nice in the sense that they are commutative. That means that I can reorder the terms of my series and I will always get the same sum. This is very nice because that is a property that we expect to have, since it is true that finite sums are commutative, right? So, this is a way in which we say that absolute convergence is much nicer than conditional convergence. So let's get started. Remember that a reordering of a series is just another series that has the exact same terms just in a different order. And what I was telling you is that if I know that a series is absolutely convergent, then reordering its terms doesn't change the value of the sums. So if I know that my series of ANs is absolutely convergent and then I have a reordering, let's call it the series of BNs, then I know that the series of the BNs is also absolutely convergent and that the sum of the ANs and the sum of the BNs is the same. And this is, as I said, this is very nice. That means that we have commutativity for absolutely convergent series. Okay, how do we prove this? Well, we're going to prove this theorem in two goes. First, we're going to worry only about the case where all the terms are non-negative, because this is a bit easier. And then we're going to use this to prove the general case. So how do we do this? We're going to assume that all my terms are non-negative, that we have that the series of the ANs is absolutely convergent, and then we have a reordering of this series, which I call the series of BNs. Now I'm going to fix a natural number k. And here is where things become very interesting. Remember that the BNs are a reordering of the ANs. So I can choose an m large enough, such that if I look at all the first m, my terms b1, b2 up to bk are going to be included in that list. So what I do is, well, I start looking, right, and try to find b1, oh, b1 is here, b2 is here, b3 is there. So I'm going to just make sure that in my list from a1 to am, I can find all these terms b1 up to bk, which is possible because remember the series of the sequence bn's is just the same as the ans but in a different order, they're just shuffled. And we're looking at a finite number of terms b1 up to bk, so they should be included in some finite set of the ans. Okay, so now because we have this, of course we should expect to have more of the A's than the B's because, well, we need to make sure that we have all those K, B's in the list of my M, A. So we know that the sum from n equals 1 to K of the BNs is less than or equal to the sum from n equals 1 to M of the ANs. Right? Because here when we're adding the ANs, we're including the sum of all the BN up to K, right? Plus possibly some other terms. And now, because we're only looking at series of non-negative numbers, I know that the partial sums are increasing and they're bounded above, so we know it's convergent, there's no problem, we renew that, and they converge to the supremum. So any partial sum is less than or equal to the sum of the series, and that is what we have here. So that tells me that the partial sums of the BNs are bounded above. And again, because the partial sums are bounded above and we have sums of non-negative terms, then the sequence of partial sums is increasing, so we know that my series of the BNs is convergent. Great. Now, we also can see that the series of the BNs has to be less than or equal to the series of the ANs. Because remember that we saw there that the series of the ANs is an upper bound for the partial sums of the BNs. And we know that the sum of the series is going to be the supremum of all those partial sums. So that's how we get this. Excellent. And now what we're going to do is we're going to reverse the roles of the ANs and the BNs. Repeat the same argument. So now we show that the series of the ANs is less than or equal to the series of the BNs. So we have two inequalities. One tells me that the series of the BNs is less than or equal to the series of the ANs, and another one that tells me that the series of the ANs is less than or equal to the series of the BNs. That means that the two series have to be equal. Okay, now that we are done with the case of non-negative terms, we need to go and find a way to use these to prove the general case. So how is the general case? Well, remember that we know that a series is absolutely convergent if and only if the series of the AN plus, the positive parts, and the series of the AN minus, so the negative parts, are both convergent. So if my series of the ANs is absolutely convergent, then we know, as I said, that some of the AN pluses and some of the AN minuses are both convergent. These were defined in a previous video, so if you don't know what they are, then try to go back and look that up. Okay, now if the series of the BNs is a reordering of the series of the ANs, then the positive parts, so the series of, just looking at really positive terms, the series of the BN pluses and the series of the BN minuses are just reorderings of the AN pluses and the BN pluses, respectively. Okay. Here's how we prove the general case. Remember first that a series is absolutely convergent if and only if the series of the AN pluses and the AN minuses are both convergent. If you want to look at a definition of this, they're in a previous video, so make sure you go there when we talk about absolute convergence and conditionally convergence. But in a way, this is just the sum that only looks really at the positive terms and the one that only looks at the negative terms. So if I know that a series is absolutely convergent, then I know that both some of the AN pluses and the AN minuses are convergent. And now if I have the series of the BNs is a reordering of the ANs, then when I look at the positive part of the BNs and the negative part of the BNs, then are reorderings of the positive and the negative parts of the ANs, respectively. So the sum of the BN plus is a reordering of the sum of the AN plus, and the series of the BN minus is a reordering of the AN minus. But now these are series of just non-negative terms, so we can apply what we just proved. So then I know that the series of the AN plus is equal to the series of the BN plus, and that the series of the AN minus is the series of the BN minus. And that means that my series of the BN is absolutely convergent, and now I can put things back together, because I know that Bn is equal to Bn plus minus Bn minus. So then we can just use now the linearity of convergent series, and this result here that we have that the n series of the n plus equals the Bn plus, and the same for the minuses, to get that indeed the series of the Bn's is equal to the series of the An.